Okay, so we're gonna get into chapter 7, work and energy. Of course, don't forget we're on the particle, work and energy. We have two different things going on. The very first one is particle and the other one is a rigid body. Of course, this is the same video that you can be able to find. I also found a cartoon, on the same thing here, and you can type it in Eureka, and it's gonna come up here by Donna Blakeney, I think. It's pretty okay to me. I mean, in a general way, that you can be able to listen to that. Of course, when we come to work in dynamics, what we're trying to do is to find out how forces in motion they connect through work. They also connect through kinetic energy and potential energy, so we will come into it as we go into the chapter. So you gotta know what is work. You're gonna get work every time a force causes an object to move. So I'm gonna go ahead and get my where is it? My pen. So sometimes it's really good to draw. So here, let's say this is your particle, and then you're gonna have some force, okay, on it. And this force is going to destroy the balance of the energy this particle is taking to position itself at that place in that space, okay? So because of this extra force, this little guy, the particle, is gonna move. So as soon as it moves, it does that amount of work. Okay, work means I move from here to here because of this force. It's kind of like you're giving an extra energy to it. So it has more energy than its own energy to stay at that location. Okay, so it moves. Like I say, we have space, and in there are many different objects. When we say object, it's so easy, and we break the objects down into particle and rigid body. Okay, it's isolates, small stuff, and you have some substantial, okay, aggregated. I would call the rigid body aggregated particles in there. When they move, sometimes, okay, the energy that they use to move, and we call that kinetic energy, can go back and forth between energy to stay, and that's the potential energy. So that kinetic energy and the potential energy, I abbreviated, K for kinetic and then E for energy. P for potential and E for energy, they go back and forth, And again, it's not only for one particle or one rigid body, it's for everything, As soon as they go into something called contact, this is called contact, a force come in contact with a particle that was, in a static or a state, where it's taking a position in the space. So the extra force is going to cause this particle move to a distance. Here, I'm just going to write a D. Some text will go with S, of course, distance. And so this distance is added to this particle. This has 0 distance. Now you add that distance, so it's moved from here to this, to another position, and because of that, the force, caused that motion. And of course, when we write it in a formal definition, it's like the amount of energy transferred by a force acting through a distance. This force caused that distance in that particle. Amount of energy meaning like I already told you, when a particle is in a position, it doesn't move. Let's say we assume the initial position is just there, sitting, and it has a potential energy of its own. This force, we have no idea where it came from. It came from somewhere, and that one already has a kinetic energy of some sort, and that energy has been transferred into this particle, so it can move. When we say transfer in, be very careful with that word, is because in fact nothing's been transferred from here to here. What's transferred is the push, contact. It got contact. As soon as it's contact, it has something called, we call that this phenomenon force, and it's going to push it to a distance. And the nature of the energy is very unique, and it's very difficult for us to physically define it. We go by contact, okay? Contact. If you contact, you can always go all the way to the very invisible, particle level that you can see, like atomic level. We can see. You might sometimes think like, if there was any physical particle at a physical state that you can't see transfer into the other one, you might think like that as well. For now, just take the energy, at our system level, at our system level. And when we say particle, is something that we can be able to detect from our system level. And when I say system level, I'm talking about the human system, because that is what you use to be able to sense your environment and everything, including what you're doing right now, learning. You're listening to my voice, and then you're looking at the slide, read, and then of course your base, your foundational pre-reading before, or something that you have already studied from high school, a little bit of here, a little bit of reading online, and you're actively doing that. So anyway, I'm talking about from the perspective of a human system as we understand about this phenomenon called force, okay? And when we define, as you know, language is very limited, very, very limited. That's why we gotta use the mathematics or physics or something else to be able to understand what really going on here, where we are. So anyway, so let's go back to this definition. You kind of get it, and you should be able to write it, in your own word. Unit of force from somewhere is going to act on a particle, because we are now in this chapter concentrating on a particle nature, with the force. And as soon as it has the contact of something, and that energy, the movement energy of this, is going to transfer to this little particle, and it will take a distance, and that phenomenon, the whole thing, we call it work, because you have a physical move from here to this position to the new position, and we call it that work has been done by that force on this particle, and what caused this motion, or what caused this distance, is this force. And when we describe it, we say in a way like energy has been transferred, and we use that energy to move, okay? I truly want you to think as you study, and don't think like you're gonna get this in one shot. No, you won't, okay? You might get what is written as a definition, but the meaning is very deep, okay? Even we study for many years, we're still trying to find what is it that we have here, what is it, this thing. Even if we try to identify or describe and put or define these phenomena in many different ways, we're still trying to find what's going on here. Truly, we don't understand. We can move a lot of the things from one place to another, because that's all we've got. That is all we've got for now. And of course we can build, we can put things together, but that's nothing compared to the knowledge of this universe or multiverses. Okay, we have no idea where exactly we are, okay, in this space that we know. And what else we have out there, we don't know that either. So the knowledge that we've got is, again, from the human perspective, it's very limited, and it's also very, very small. Yeah, even though it is small, it is something, because we can be able to do many, many things with it on this planet. Yeah, so let's go back to, now we're going to put that definition into mathematical language. Of course, in math we use symbol, symbols, and we call, okay, it's going from 1 to 2, and here's the energy. And we're going to go this distance from our former distance R1 to the next distance R2 with this force, right? And every time you, this little differentiation means you're studying against, you're studying the force against the distance, because you have two things going on, your force and the distance, and the distance that changes according to that force. So they're very depending, so this distance is depending on that force, by the way. So that's what it practically, the whole mathematical equation or formula, all the meaning of these symbols is telling you exactly that. So I am depending on the force, and I move from here to here with that energy. Okay. And of course, even though we say energy and work like very loosely, if we have to formally use the word is going to be work. Work going from one position to another by using that force. And of course, R mean like we're taking that distance. So make sure you study that. Yeah. All right. Then, of course, every time you use a symbol, you have to define what that is. You can just say like, oh, I don't know. So you have already defined U is for work, and F is for force. We have many different kinds of force. We have component force, and we have the resultant force, and this one is the net force. Net force means there can be sub force underneath causing the net force. So net force being applied to the particle by something external, to it. External mean it doesn't come from within the particle itself. It's saying it comes from the environment, on it. Then, of course, your R is the position factor of that particle. Then this is the same equation, And here, of course, in this slide, we emphasize work is a scalar. It doesn't have direction, Doesn't say, you don't have to define the direction, because your force is going to take care of that direction, Force and work is related completely, because of this force, work is done. So therefore, the force defines the direction, and you don't have to worry about, we're going to just take care of the magnitude of how much work has been done on that particle. So work is, sometimes we write it very simple way. Of course, if you write it simple way, then you lose the accuracy or precision like that. Force with a distance, because of this force, the distance has been made, and FD you can go. Of course, this force can be defined in many components. Even though we talked about the net force, it can be calculated if you come to the complex system, because you're don't forget where you are. You're at the first level, dynamic 1. Okay. The class is non-proportional. You have like many different ages and many different backgrounds, and very greedy students are, and they don't know where they are. That's another issue in the class. So you gotta understand like the content of this course is targeted to 18 or 20 freshmen and sophomore, okay, college student, right? So that means the first 2 years of your 4-year degrees. You can't expect too much out of it, and in that 2 year, you are satisfying the foundation of the dynamics, okay, that you can be able to improve upon it. And of course, some of you are like way over here from with the knowledge that they already got from somewhere, I don't know, and then they're applying that into the course, and there goes a confusion and issue in there, So try to clean your slate for now, and then go back to the very freshman. Try to play your role as a freshman student and take it everything from the very basic, and then you're gonna go from there. And then do not disrespect professor just because they're Asians or they're Mediterranean or they're Indian or so and so. They have studied numbers of here, I would say, definitely more than you. They have, serious knowledge. Some of us don't even share that. Of course, there are professors who come from industry. Those kind of professors, you can't count on them because they're not academics. They only know how to do their job at that company, and they can do it because of the experience many years, like 20 years, 30 years, doing the same thing, and they understand the related knowledge. But they're not academic. There is a big difference in academic professors and industry related instructor or professor or lecturer. Very different mindset, very different goals. Ours is scholarship. Scholarship doesn't mean that you can't survive out in the world. No, we can survive. We just don't want to be in the world, because we found something that is more than the world. So university, like over time, the true meaning of university, like my professor taught me, you lost it. University, you don't come here to find a job like we're practicing right now in this modern world. University is more than a vocation, more than a trade. It's where university is what we're trying to study who we are, what we are, where we are, and what do we have here, and trying to actually solve this mystery of the whole thing, from many different subjects, of course. And that's why we call this philosopher, not just a professor, but you go into something called philosophy, not just to get a degree. Degree means nothing to us. What matters to us is to try to understand this thing that is bothering us for many centuries and years. That is called scholarship. So you gotta try to analyze yourself, where you want to go, what you want to do. And of course, and because of the government changes, civilization changes, and all of that, the university become a salesmanship. You're getting into the salesmanship instead of the real academic and scholarship. The salesmanship and trying to sell this enrollment program, everything, and that's where all that industrial, people come in and mess the whole thing up. So make sure that we have a two seriously different group with seriously different goals within the colleges and universities in the United States and the world. And so I stand on scholarship because I sacrificed my life, I sacrificed my money, I sacrificed my family, I sacrificed everything, for scholarship. That's for school, for you students, and for my own curiosity that we study these subjects, not just to apply to the real world knowledge. Of course, we mainly teach that to students, not to become a servant. Actually, no, actually you're more than that. You're more than the workforce, by the way, even though you are attracted to the money. But I would say at least 1 out of 100 students, 1% or less than 1%, they're gonna come into this academics, whatever reason that is. Even in academic, there There are many different groups, okay? Academic for the money, academic for the politics, academic for the community, academic for themselves, and the academic for academic scholarship, okay? And that is less than, I would say, 0.1% of the PhD population. Yeah, so just try to analyze yourself. The first thing that you gotta judge is you. You gotta judge yourself, know yourself, understand how you as a person or a system works, and go from there. What do you want? I just want to get a job. I just want to follow money. I just want fame. I just want to become a professor, to do politics. I want to have a status. I want to just do work outside as an engineer, as a specific role related to our major, and then you're going to make money and make a better life, a quality life. Try to analyze that, okay, in your first year, please. Okay, so 18 to 19, your first year, and the second year, of course, I shouldn't say 18 to 19, I would say the first year and then the second year, try to analyze. Of course, the older student doesn't really matter, your first year, second year. In first year and second year, that's what you do. Analyze yourself, analyze your goal, analyze where you want to go, okay? And don't be confused about it. And then get into the study, okay? So now let's go back to the units of work. Let me erase this board. Okay, so now after we know what we're doing here, scholarship, and here work is a scalar, after I talk about all the scholarship means your profession is to study something. Now let's go back to work, and work depends on the force and making a particle or an object taking a distance. Of course we write it like this, integration, operation for that. Integration, we're integrating, we're like studying how much distance has been made according to that force from this place to another place. Okay, so first distance, second distance is going to give you the total distance that this particle has traveled because of that force, and we call that work. And the work again has no direction, and it is a scalar. Now getting into the unit, so when you go into your unit, we have this joules, J, of course that's your force, and this is your distance, so therefore distance is length in meter, your force is in Newton, so Newton and meter is going to give you joules. Kilo, calorie, kilo and then calorie is about 4,187 joules. British thermal unit, B for British, T for thermal, and U for unit, and that's about 778 feet, okay, pound. Then if you convert from here to here, you're going to get about 1055 joules. This is just converting the one unit system to another. Then we will go into work done by a constant force. Your chapter 7, 8, 9, okay, you don't have very heavy calculation. I mean, the entire course doesn't have heavy calculations, only very simple calculation we have selected that you would do at your first level of dynamics, okay? So we go back to the force, okay, that causes a particle change in position, and that much of distance it went, and we call that work. Of course, this is just converting or doing our integration, operation. We take this out because it's constant force applied to that, so, and we integrate this R, and when you integrate it, of course, we get this. And that's pretty easy. Your force times second, position minus your first position will give you the total distance traveled. You can also write it in this symbol. So your work is force time change in position. position 1 to 2 has been changed. For components, sometimes if you have an angle, your force is not just linear, but it has an angle like that onto a particle. Then of course you have to come up with your sine and cosine depends on your triangle. Again, we're not going to get into this for complex calculation. They're not very complex, by the way, even though certain people in the school see them complex, but they're definitely not complex. It's easy and you can handle it. Okay, I have no doubt. I'm very confident that you can handle it in dynamic 2, 3. Okay, if you don't go on to dynamic 2, 3, like there's one student who is always negating what I'm trying to say, then you're on your own. You study by yourself. And a lot of the professor, we're a great advocate of sharing knowledge to everybody, anybody outside in the world. And if you want to use, if you're against S and you don't want to use and disrespect the professor at your own school, then it's up to you. Okay, it's up to you. You can study whichever professor, whichever textbook you respect. But we have to do our job here. And I just want to say that at least we deserve that amount of respect. Okay. And it wouldn't be fair to thank the professor in a very, very horrible way. Your description about a professor is not who they are, even though I'm putting it directly, of course, because I'm hearing some things going around in the school. So the judgment by the student toward a professor can never be right, because number one is they don't have that ability, and even though they have the ability, still is not mature, and also very contradict. Like sometimes a lot of the people at school lack of education, even though they are the educators, because sometimes they forget to think about how contradict it is, the situation that they present from different point of view in terms of administrator or in terms of student doesn't matched. Okay, it's just so chaotic. And when the system is very chaotic, a lot of corruption can happen, a lot of bullying, or a lot of things that ain't correct can happen in those kind of system. It's not good, and we shouldn't do it. Okay, you guys need to know that when a professor take a job, they aim to do the best work they can be able to give it to you, regardless of how you judge them or even say horribly against them. Their concentration is you. Okay, is you and how you're studying. Of course, professor, they can't serve everybody, because we're dealing with a very diverse, student body here, and it isn't easy for any one of us to be able to teach very diverse classroom, and very stressful, by the way, every day to take care of everybody whose background is not the same. It's not easy for us to do that. So we also deserve a little bit of respect for that kind of work. So just be kind when you judge somebody, because it isn't fair to their work at all. They're giving 100% of themselves into the education. And another thing is making things up, something that isn't even true. That gotta stop. That goes into I would say, I don't even know how to put that in words. The things that isn't true won't be true. Okay, and you shouldn't say it against another person without the knowledge of what is the truth about that person. So just refrain from doing it. It's not fun anymore. When you cross a line, so make sure that you keep student conduct according to the policy. Every school has a policy, and behave within that boundaries. We have boundaries. We have lines. Okay, we don't cross them. And when you talk about a professor or your classmate, and just be very careful of what you're saying about them, okay? Because it isn't fair to them. It isn't fair to them. Of course, I will give you an example. This comes from a recent event, even though I will put it very indirectly, and I believe that my students will like learn from that kind of situation and understand their own behavior or actions, towards the professors, and take care of their own behavior and actions. If you how What kind of institution would be that they hire a professor and that professor is acting like a lunatic, teaching the things that doesn't really make sense? Maybe it doesn't make sense for you with your brain. Don't you think that administration something's wrong, right? Why would they hire such a person to manage a class or teach the subject that all other professors refuse to teach? Okay, so I don't know. It's a very very funny thing that we're facing in many of the university. A lot of the seriously difficult subjects are taught by first generation professors, and not many generations professors here, by the way. Okay, they always teach it something that has a lot of equipment or hands-on, easy to teach, I would say. And the rest of the theoretical stuffs are taught, I would say, not 100%, I would say about like 80% are taught by the first generation professors. And that's kind of odd in our system of education, okay? I don't know why, but it is the truth of it. They always avoid to teach the very difficult subject. And of course, I also have to take care of the difficult subject because I have no idea why, okay, like Asian professors or Mediterranean professors, we always have to teach the theoretical stuff, always, without hands-on, or the least number of, not like, I would say, like how unfairly the job tasks are divided, even among the professors. And of course, we also have to fight for it. So let's go back to this contradiction. So why would you want to judge so horribly against this group of professors while they were hired actually by the school, right? Themselves. If they sucks that much, then why were they even hiring them and let them do the difficult subjects? Doesn't make sense to me. Very contradict. So just be kind in your thoughts and don't abuse, okay? Don't abuse them, or don't abuse by saying horrible things, like saying gossip between students, saying the words that can influence another students against the professor. Should not be done by the students, okay? So make sure that my student, you guys, are not going to do these things, because it create, okay, they create issues in the system, serious issue, because those kind of professors, they will fight, okay, fight you back, and you don't want to attack other professors, okay, in such a horrible way, because they're gonna do 100%, and when those kind of things happen, because it isn't fair to them. Also, it isn't true to them. There was a student saying, like, I would be staying. Okay, this I'll give you example. Like, I would be in my office, but I refuse to see the student because I'm afraid to meet that student. Why would I do that? I'm always in my class, in my lab, or in my office, and you can find there is a secretary. Secretary is pay a lot of money to sit there at the desk to tell you exactly where they are, because she knows, okay, or he or she knows in the office. So make sure you go there and talk to them, to find where's this professor or that professor. They will guide you. Why didn't you do anything? You can knock on the door, but you assume that out of all the possible reasons, you assume that this professor don't want to see you because for some reason that you just exaggerated, talked outside, even laugh about it. That crossed the line, and never ever do that again. Okay, don't do that again. We have passed. We have passed so many tests on the subject we study. You're studying only 1 year here with one course. We have done that for at least 8 years for a professor to become a professor. Okay, even if you come from industries or academic, they have many years of experience and many years of study on the same subject. They know, okay, seriously know them. That's what we call profession in scholarship, or profession in a subject, or profession in the work, okay, that they do. So please, okay, I'm just gonna close on, because that is in my head for like 1 week, so it comes to the point that I have to talk to my students to behave, and don't overdo and don't oversay things that you're not sure about, and don't laugh at a professor just because a professor may be younger than you or may not be younger than you. And okay, there's also age problem. Like when a professor appear to be young or small, and they wanna say harshly on the professor. If the professor is a woman professor, a woman professor always get hurt more than the man professor. And that's why we have this group like women in engineering, women in technology, seriously being protected by many people, okay, in this institution or at work because of those kind of pressure by the environment. So anyway, so the classroom management, and what I really want to tell you is, just that, not naming anybody here. Yeah, everybody. I love my students so very, very much, and my concentration is your success. I would never do anything or yes, to disturb that success. Professor would even give you, more than you deserve, by the way, in terms of grade or anything, your effort, because we understand how difficult today for the student even to stay or come to class. Very, very tiring. We understand that. So also we expect a little bit of understanding from your side towards us. Okay, every day we have a lot of work. We're not working from Monday to Friday. We're working Monday to Sunday, non-stop, by the way. If you don't believe me, you can come and stay with me 1 week and you will understand how we're rolling every day, okay? For you, for school, for ourselves, of course, and everything. It's not only job, it's the whole thing, and the whole system, go all the way to the government or federal level, even state, yes, local communities, and everything in it. It's a very complex system. So anyways, just be mindful about what you are saying and how you are saying in class, okay? If it was about the professor, either me or someone else, okay? I'm just giving you a indirect example. Okay, so now let's get back to work done by a constant force. So now I've already explained each, okay, equation. You only have to recognize it, since the quiz is completely open book and is with unlimited time, even giving you 2 attempts. So you shouldn't have any kind of issue, to just, so the first year is just you trying to read these material, reading material, listening to what they are, and of course we attempt a little bit. I'm just throwing a little bit of calculation for you guys, because some of the students want to do it. Okay, of course, giving you the simplest equations. So don't also get confused with, this is just integration. It's just telling you, hey, we're doing our integration. I even allow you to use your AI if you want to. Okay, all you have to just type it in or write it in or copy it in. It's gonna give it to you. So don't feel so stressed about it. Of course, you do need to understand, at least the phenomenon of the forces, or the work or position. Okay, how energy can be transferred and also can be stored. Okay, and all these things you need to know. All right, at least a foundation, the basic knowledge you got to get it out of this class. Okay, and this is your, again, force diagram, and we are going to put the mathematics. So first we define by using English, then mathematics with symbols and operations, and then we come into diagrams. A diagram is visualization and makes you understand the situation, yeah, by using these cartoon, diagrams. So here is your force at an angle, theta, yeah, this is cosine of course. In this case, if you have many different triangle like this, when you draw it, it can be like this. Sometimes your force is that way. It's not always perfect angle like that, or 45. A lot of the textbook use this angle like 45, 30, and 60 to make the sample equation, sample calculation easy. Of course, this angle can be even point something, 0.5 or something. So anyway, here is your diagram, and here is your axis, y and x distance that this block is going to move, from here all the way to here. It is measured by the beginning of the block, and here the beginning of the block. Okay, so it moves from here all the way to here. And with a velocity just showing you that it moves. There's a motion. We call velocity the motion aspect of the motion, so therefore, or character of the motion. So you can look at this diagram and understand that this mass of this block with this mass is going to move from here all the way to here, that amount of distance, okay, with this force. And the work has been done, force time that distance, okay. Of course, the force is at an angle, so we are going to use F cosine theta. And D move from position 1 to position 2. Of course, this velocity, you can turn it into acceleration, so therefore that can be able to relate to that force anyway, yeah? So the mass is going to move with that acceleration, this distance, making that work, okay? Some people like to write W symbol for work, and it's okay, it's up to you, whatever you want to do. All right, then we're going to take a look at work done by a non-constant force. So in previous slide, we look at the work done by the constant force. This one is not constant. Again, it's not covered in your complex, calculations are not covered in this course. So all you have to do is just to take a look at it and listen at least one time. No need to memorize, There are about 3 students, I think, want to memorize everything, and you don't need it, okay? Just read it, and I'll give it to you, the access to the textbook. I try to find something that you can be able to access and free of copyright, so they can be able to, like go back to that textbook if you want to. So here the same thing, position 1 to position 2, going with this force, and you have done that amount of work taking this distance, okay? And of course, after you calculate it, we break it down into components because you're studying the force with the xy coordinate, okay? Things are happening that xy coordinates when we look at to calculate the magnitude of work. So in there, since we want to calculate the magnitude of work, we are going to do some integrations, and then we're going to do some breaking that net force into component force, So we go with the dx and the dy of that force and turn it, the whole thing, into this equation. That's all it's telling you and show you step by step how we operate it. Of course, right now you don't have to know. You only have to know line. We can be able to represent this work in terms of FDR. We can also represent that work in terms of the axis, okay, components of the force, okay. Because it is the same thing, you going, R1 to R2 can be represented by these coordinates, corresponding x and y coordinates, and that's exactly what we're doing here, Then of course we come into anti-coordinates. We don't cover anti-coordinate system in this course, so you can only read it. We do the same thing. This is our basic equation, and we do that operation, and we defined, all right, FR into F and S, which is your anti-coordinate, right, on axis. It just instead of xy, we have an anti, okay. And then of course we write instead of R, we write S, okay, in the anti-coordinate axis. Then we go into example 7.1-1. And here, all you have to do is just to understand again another reading to see the equation and to understand if your force is constant or not, because we just study work done by constant force and non-constant force. So that's the first column according to this equation. Here you have your Ft cosine, meaning like the force is at an angle. And we have also Fr and Ft, simple equation for work, and your integration equation for work, and another integration equation for work. This is just showing you as a vector because see the bold, and this is just showing you we're concentrating just the amount, which is magnitude. So your F is constant, yes, in this equation, the force at an angle, and here too. Here we're integrating, so therefore you're dealing with the non-constant force. Here F is in the direction of R, so this is your motion, a distance, movement is along that line. And of course, when we think about F is a vector because it is a force, and we're looking at the net force, right? So therefore, your net force direction, F is in the direction of R, and that's not necessarily true, because your F is going there and your force can be going horizontally, your position of that moving particle can be in that direction. So not necessarily true here, so therefore we put it no for that. Of course, for this, yes, and it is going in that direction because see, like we don't have the angle because you're going that way, yes, so your R is going in the same direction as your force. For integration, non-constant force, the same thing, direction, yes, we can't really say like they're in the same direction, F and R, and here it is in the same direction. So that's because we're just dealing with the magnitude here, so therefore the direction is in the same direction automatically. That is in the assumption. Here is, of course, you have a different direction because we have no idea which direction your F is applied to that particle. It's not defined here in the equation, so therefore we can assume, we can't define that F got to be in the same direction of R at all. At least you should know that much for this table. This is your example 7.1-2. You only have to listen and I'm going to go over that. So here we have a particle, and that particle is being pushed, and it is being pushed along a frictionless surface, meaning like we don't care for the friction, so just get rid of one force acting on that particle. And then of course I don't like this diagram because we're showing the particle like a rigid body, see, like a block. So it's okay, we just take it, this is a particle mass, and then it's going to go from the position x1 to x2. And of course you have to draw that free body diagram of that block. So let's see how we're going to draw that. Okay, here is your free body diagram. So we have a force, particle, weight, mg, direction going straight down, your normal force, which is resisting that weight, okay, and they are in balance. Without that, your particle will not be able to take a position on this planet. Planet mean our planet Earth here. And this balance, action and reaction force the forces are very, very important to define the position. Of course, there's the external force, and this is what we're going to concentrate to understand how this particle is going to move. It does move because of this external force, yeah, position 1 to position 2, because it said it so here in your description of that condition or situation, yeah, going from x1 to 2. So now we got the diagram, and the question asks you, what is the resultant force that acts on that particle? So we have to find the resultant. The resultant force will be calculated because you're dealing with the two x's. So we have two, if you think about z in three-dimensional, we have I, j, and k unit vectors, yeah? So the p is going in the x direction, so you will multiply with I unit vector. This is y direction, has two forces, your weight and then your normal force. Normal force minus weight, which is mg, okay, is going to give you the resultant of this guy, and then times you have a vector, unit vector is j. That's just showing you the direction, yeah, whether you go down or up depends on the amount of force that you have here. Anyways, that is your resultant force. You can be able to calculate this way, okay? Then we have to calculate what is the work done by force, this force, on that particle. So we gotta figure out the distance. So to calculate, yeah, to calculate the work, we're gonna bring our work, which is this, okay? I'm gonna show you our table again so you kind of get it. This table, yeah, and it's right here. So you know that our force is not constant, and your force is not in the direction of r, okay? Then after reviewing our table on the force and the direction, you're gonna put this, yeah, the one that we have just calculated for force magnitude, and then your r, okay, is gonna be this, because your r is, if you think about your y and x, I have shown you several times, yeah. So if your r is like this, you have a point, two endpoints, and it's gonna relate that way and this way, yes, and that's where you get your y1, y2, and your r. If we just make a simple problem here, see like how the corresponding coordinates are around that distance r. So when you have r1 and 2, it has a component of y-axis and components of x-axis, and that's what we're putting that in. All the x-axis has a vector, unit vector I, and a unit vector j for the y, yeah. So that's we ended this way to take care of the direction, yeah. Of course, we are in differentiation, so every time we break the component, we do the mathematical operation differentiation. Every time we study, you know, work, we're integrating. Don't forget, you're back and forth, you know, going that direction forward. Differentiation and coming back this direction, integration. Yeah? I just write that down. So don't forget it. We go from the position to vector, vector velocity, and then vector acceleration. Then coming back from acceleration to velocity, going back, yeah, to position from velocity. So don't forget that, and that's exactly what we're doing here, yeah. And operation wise, so we're integrating the force to get the work, okay. Then we did the integration operation to go from here to here, and that's completely integration operation in mathematics. We have many different integration rules that you need to study. So don't ask me going from here to here. I'll have to lecture you the entire calculus. It isn't fair to me to teach you everything that you didn't learn before coming into dynamic class. And it isn't your fault either, and that's just a system fault because the curriculums and everything are written that way, not very perfect. It isn't their fault either because the entire system's been like that, for a long time. But we're gonna do the best we can with what we have. So just understand that going from here to here, you have to study a series of calculus rules. Some students, of course, have curiosity, so they will attempt to do it, and I totally encourage you to do that, and I have a confidence that you can be able to do it. So do it over the summer and get into these calculus 1, 2, 3 rules to do this. You can also use the AI. AI is very good to support your study, scholarship. So use it. Also be very careful and mindful about some of the AI will give you a wrong result of whatever query that you are typing in. But it depends on how you type it as well. So x1 and then also x2. Then we do the integration and we get this result. So here is our P, your force, and then we're going from x1 to x2, and that's the result of that distance. So at the end, you get the simplified version of the force time distance, which is a change in position. Will give you the distance. So that's your work, okay, how to calculate it. So at least you gotta get this and that, okay, at the end. How you write this distance from here to here, of course, we call it R or X. If you go with X, you know that, how we go on the X direction or Y direction, things like that, Okay. And this is just a multiple choice questions. It's asking you which of the following statements are true, so we go one by one. The very first one is the work done by a force F acting at an angle to the displacement delta x is equal to like this, okay? We can say that because you have an angle, so we also have to account for that angle, so this is eliminated right away. The work done by another one, the work done by a force pointing in the direction of the displacement means you're just taking a distance, is equal to, of course, your work is equal to F change in the distance. That is correct. That is completely correct. The work done by a force F that is perpendicular to the direction of the displacement, yes, and you have a displacement delta x is equal to 0. This is also correct because it is perpendicular, so therefore you are not going to make x displacement in that direction, x direction. 0 means you're not going to go that direction because it is perpendicular like that, forces. It won't go, And the last one is the work done by a force pointing in the direction of the displacement. Delta x is negative. If it is going to point in the direction, if your force is in the direction of x, it will go in that direction, from the table. It's already told you about that, so it can't be negative because they're going in the same direction. So therefore this is wrong, So this 2 is right. It's correct. Then we get into 7.1-3. So here you have to think about a particle being pulled up a rough slope. So you have a rough slope right here and draw a free body diagram of the block. So the question is giving you that, and you have to draw a free body diagram. A free body diagram and a regular diagram. This is not free body diagram because it doesn't have the axis. They have to bring a different axis in there for you to be able to draw the free body diagram. So let's see. In here, this is called free body diagram. That's just a regular diagram, okay? And this one is a free body diagram. So you have xy is right there. Your force at an angle, we account for that. Your mass, so therefore it has a weight. Your motion path is going that way, yes. So therefore, because you're pulling, yeah, up the slope, so your horizontal alignment right there, yeah, and of course, your normal got to be perpendicular to the horizontal alignment of the force. You're gonna put your normal force, yes, for that. Normal force is not against this, okay, because this is straight down, yeah, to the gravity or gravitational force. And you have normal forces depends on where the ground is for the object, yeah, to stand upon. So just be very very careful when you determine the normal force. Of course, we are very familiar to drawing like this all the time, yeah, straight down. So your mg, and then n. Of course, in this case, your normal force and the gravitational force are the same. So then we're going to have a friction. It doesn't say, your problem doesn't say friction is neglected, yeah, so therefore we will have to account for it. So every time you read the problem, every sentence that you read, make sure that you understand what you are reading, and I talked about that almost every time, yeah, you go into the problem. Of course, so right now you just listen. I might ask you to draw the diagram, but I'm not going to ask you to calculate. Okay, at least you've got to come up with this type of free body diagram. Yeah. Okay, the phi main line, there's an angle between this guy and that. Because it's not 90 to 90 anymore, there is a particular triangle like this. Okay, so this angle is not a phi. Yeah. We have to account for every angle that is resultant in the free body diagram. Then we come into here and we calculate work done by the force on the particle. And of course, we will use components. Okay, so we have the first one, which is this guy, second one, which is that guy, and the third one, which is F, which is your friction. This is cosine, is because your force is that way, okay, and it is an adjacent angle. This theta is adjacent angle to the force, and here is the opposite, okay, because when you look at this, because the resultant, yes, is gonna go in that like this, okay, so vector starting end, and then on the end point of the second vector, and start the end point of the first vector with a start point of the second vector, and go there. So your resultant go from here to there. If you want me to draw, it would be like this. So your resultant is like that, and your angle is right here. So therefore, this resultant is sine, yeah, from the angle. So again, that's your trigonometry, okay? And if you ask me to teach you trigonometry, I'm just going to, stress out, I guess, because it isn't fair for us to teach all the calculus, all the trigonometry, all the geometry you have never done in high school, and I have no idea what you're doing from K to 12 either, What did you learn in high school from kindergarten all the way to the end? That's 12 years of study. You should master trigonometry, a little bit about calculus. And I am really, really shocked that they didn't teach you that, by the way. Linear or algebra. Some of the schools don't even teach you algebra. I have no idea what they're teaching you there either. Just talking. They know how to talk. That's about it. Cosmetic stuff. What you really need the mathematics, by the way. Otherwise, it's really difficult to follow your STEM. That's why I heard many times a professor is saying, the student don't know anything about technology. Maybe they do know a lot of technology, by the way. I shouldn't say technology, but science and mathematics is very, very low, in ability. I have no idea why. But then you need science and mathematics to branch out into engineering, and then of course technology. Right now is a reverse, like high school students know because they want to hack into other systems, so they do like coding or Java scripting to harm other people's computer or cell phone. That's about they do, the real thing in science and mathematics is just not in the head. So anyway, so try to review your trigonometry to be able to see what's going on with this angle. Yeah, I am giving you little by little for at least on this problem. And then of course we do our FDR. Yeah, put it in. Don't worry about the integration, and you're gonna end up getting that. I'm not again asking you these things. Yeah, at least you should be able to draw a free body diagram. Then we get into our multiple choice again for example 7.1-3, and which of the following statements are true. So the very first one is the weight force of an object never does work. That's not true. This is out right away. Weight of an object never does work. That's not true. If this weight overcome the resistance, force, which is opposing it, it would definitely take distance down. So you will have a work. So weight is counted as force. The distance that whatever object here that it will move is going to be, or itself, is going to be the distance. So this F and D will definitely produce your U, which is your work. So that's not true, eliminated. So only the component of the force in the direction of the displacement does work. That is correct. Yeah. So if you have a component of the force in the direction of the displacement, it does the work. Yes. In order for work to happen, you have to take a distance. When you take the distance, of course, your force is going to go in that direction. So this is correct. The work done by a force F pointing in the opposite direction of the displacement is negative. Yes, if the force is going that way, and if your delta x is going this way, and they do have a delta x as the negative, meaning it's not just one way or the other. Negative meaning you are in an opposite direction to where this is going. Yeah, so therefore this is correct. So A is wrong, B, C, they are correct. Okay, so I'm gonna stop the first lecture. I'm trying to cut it like 1 hour lecture each, and we will go into 7.1-4 in next video.